Okay. I know it's not like officially class time yet, but wow, it's 2 whole minutes. That's a long time. So they might have a good joke.
I mean, it's longer than that.
Isn't that funny? Isn't that funny? I always have the best jokes until somebody says, tell the joke, and they're like, oh, no joke. Why did you cross the road? Oh, we don't even know the answer. What? Yeah.
Knock, knock.
Who's there?
Interrupting cow.
Oh, that's interesting. Haha, funny. Yeah, I don't know if it's because I figured that one out or if I've heard it before.
Jacob, tell everybody the joke.
I should go with the preceding one, but I know where you were going with that. Tell the joke. Tell the joke. Who's got the joke? Who are you saying?
Yeah.
Okay, oh, you got the joke.
Okay, so a guy in Saran Wrap walks into a therapist's office. What does the therapist say? I can clearly see your nuts.
Okay, that was inappropriate.
At least mine was.
You have to leave. Okay, so now my watch says 11, so we're starting and we're not telling any more jokes. The only jokes that get told now are my bad jokes. Shut up. Okay, so if you did the pre-lecture, how many of you did the pre-lecture reading? I'm so happy that I am making those promptly. Actually, I forgot the last lecture and nobody scolded me. That's how I know you guys are excited. But I try to have them up by 7 p.m. the night before, and it's a good idea to have a look at it. Otherwise, I'll quit. Okay, so if you read the pre-lecture reading notes, then you know that what we're going to do today is finish up Spinors to the best of our ability, and then we're going to move on to action principles, and then that's eventually going to segue into the equations of motion for various types of fields. We'll look at scalar fields, spinor fields, and vector fields, what their equations of motion look like. And the way that story plays out is very beautiful. We'll start with just free fields that have no interactions. We'll look at what the equations of motion look like, and then we will introduce interactions through the principle of local gauge invariance, and that'll be a really nice, very beautiful part of the story of particle physics. But we have to finish up with spinors. So picking up where we left off last time, golly, I haven't said anything. How do you possibly have? Yeah, what?
So it seems like we use the poly matrices in like these new type of generators we're using. Is it nice that you can use them in all 3 different dimensions? Like you can always pull out poly matrices inside the generators?
Sorry, you're saying generators and then poly matrices?
Yeah, so like we use we have the Dirac generators and mathematical.
So we have the Dirac matrices, and then we have the generators that we build from the Dirac matrices, and it's important to keep them distinct. So the generators are these sigma mu nus, and these are defined as minus I over 4, the commutator of the Dirac matrices. Matrices. So the Dirac matrices by themselves are not generators. Okay, it's their commutators that form the generators of Lorentz transformations as they act on spinors.
Okay, so in higher dimensions, do those matrices exhibit the same behavior we're seeing like you pull out poly matrices from lower dimensions?
Yeah, actually the way that you work with Dirac matrices in an arbitrary number of dimensions is you take your dimensionality, and I briefly alluded to this last time. So if you're in 4 dimensions, you basically take all of the independent planes, and for each independent plane, you basically introduce 2-component spinors that are governed by Pauli matrices, and then your total space-time is just described by all of these pairs or all of these sets of Pauli matrices. So the gamma matrices, since we're in 4 dimensions, if you write them out, they're actually written in terms of the sigmas. And if you're in 6 dimensions, your gamma matrices would be 6 by 6 matrices that again use sigmas in different places. So the fundamental sort of building block of spinors are 2-dimensional spaces, little 2-dimensional planes, because that's the minimum you need to specify a rotation. You get sigma matrices, Pauli matrices from each 2-dimensional plane, and then the gamma matrices are just building those up and pairing them up in higher dimensions. Yeah, that's exactly the way the story plays out. We're in this class, we're not going to go beyond 4 dimensions, so we won't need to mess with that. Okay, so last time we were trying to build an invariant from spinors, and recall that our invariant if we construct it right, would look something like that. And we tried, by analogy to what we did in the three-dimensional case where our spinors were the SU2 representation of SO3, we tried to say that the dual spinor was just a complex conjugate of the original spinor. And we found that this failed, okay? And the reason that it failed, which I showed you last time, was essentially that the, even though the Pauli matrices are Hermitian, the gamma matrices are not. Okay, and more importantly, actually, hold on, is it the gamma matrices or not? No, they're not. Okay, but more importantly, in three dimensions where we built the generators sigma ij out of commutators of the Pauli matrices, the generators themselves were Hermitian. So sigma ij dagger equals sigma ij. But in four dimensions where these are built out of, and there's some like minus I over 2, I don't know what the coefficient was in this case. It doesn't matter, we're going to work in four dimensions. Using this definition of the generators, we find that sigma 0j dagger came out to be minus sigma 0j. So if you have one time component and the other spatial, then you're anti-Hermitian. However, if your indices are purely spatial, then you're genuinely Hermitian. Okay? And the reason that was, yeah?
I thought we built sigma mu from.
Sorry, you're right. I'm getting sigma crazy. I'm just like sigma and all over the damn place. No, yeah, from the Dirac matrices. Thank you. And the reason this is important is because if we want to try and build this guy by saying this is the transpose of the complex conjugate, so we try that for our dual, then when we transform this, the transformation of this and the transformation of this do not cancel each other out. Yeah.
It seems to me as though your definition of sigma ij would imply that sigma ij and sigma I can't be Hermitian.
Sorry.
The sigma ij is Hermitian, then some sort of non-Hermitian part of sigma I has to cancel out the fact.
Yeah, no, you're right. And no, actually, yeah, that's a real coefficient. We get a complex coefficient here precisely because we're working in the Minkowski space metric. Okay, and you've got a -1, 1, 1, 1, 1, 1 that you have to accommodate. Okay. You're right. So here the Hermitianality of these imply the Hermitianality of this. But here it fails, particularly when you have a gamma 0 in there. Okay, you can review the explicit expressions for these and see the details. But for now, remember the problem here is that if I transform this guy, then this is e to the I over 4 sigma mu nu omega mu nu psi Hermitian conjugate, and then this is e to the I over 4 sigma mu nu omega mu nu psi. I just transform this with the usual spin transformation, take the Hermitian conjugate, and then transform this. And the issue, as you can see, is normally, as usual, if you transpose two things, you reverse their order. And we see the issue, right? If this were Hermitian, okay, then taking the complex conjugate of it would not change it, and so the only thing that would happen is there'd be a minus here, and then this whole thing would cancel this. But these are not Hermitian. They change. In fact, one of them changes sign. Okay? So this is not going to be a good invariant for us. But it does at least give us a little hint as to what we need to do to fix this. Okay? The problem child is this particular transformation generator, one that involves a 0. So we might think that we're going to have to introduce something involving something 0 in order to get an object which is truly an invariant, and it turns out that it works. So with no further ado, let me show you a correct construction for an invariant. So if we take as our dual the complex conjugate times gamma 0, okay, there's that special thing we're going to work with. A priori, doesn't make any sense that this is going to work out, but we'll see that it does. Then what we can do is we can construct this guy. So actually, let me write it this way. And I totally wrote it wrong. I left off an I, and that was my bad. Okay, so psi dual is going to be psi star multiplied by I gamma naught. Okay, and this just makes sense because this is a matrix in spin space, and this is therefore a code vector, and so matrix multiplication makes sense in that context. So now if I form the transpose of psi twiddle and psi, then I have I gamma naught psi star transpose psi. And let's see how I want to do this. Yeah, I'm going to hang on to this guy. So I gamma naught, I psi dagger gamma naught transpose psi. Now, does anybody have the form of gamma naught in front of them by chance from your previous notes? Yeah, it's symmetric. Gamma naught is symmetric, so the transpose is the same as the original thing, so there's really no reason to specify transposing it. And now what I can do is I can transform this. So if I transform this, then everything gets transformed. Okay? And now we just stick in exactly what we did before. So this looks a lot like what we just did. All right, you Hermitian conjugate that, you reverse the order. Okay. So what does that do for us? Okay. Well, I am not going to show you why, because you're going to do it in your homework. And if you've looked at the homework, you've already seen it. But this guy right here, it turns out is exactly gamma naught e to the minus I over 4 sigma mu nu omega mu nu. Yeah.
So what's the point of multiplying by I?
What is the point of multiplying by I?
For the dual vector.
For the dual vector? There are different conventions for the gamma matrices depending on the sign of the metric. Essentially what this is going to do is it's going to make sure that this combination gives us something real. Off the cuff, you might think just doing psi star psi would give you something real, but remember this can be complex. Or it is a complex. What's the form of gamma naught? Is it complex? Yeah, so the I takes care of the complex elements in gamma 0. If you worked in a basis of the gamma matrices where this is real, and there's certainly a choice where it's like that, then this definition does not have an I. But the goal is to make this thing real. Okay? So, does everybody see the magic of this? I mean, this step is not trivial, and you'll do it in your homework. Okay? But with that in mind, then this expression just becomes I psi dagger gamma 0 psi, because these two exponents exactly cancel, and then you can work backwards to show that that's exactly just psi twiddle transpose psi. Okay? All right? So with that in mind, what we're going to use is what is sometimes called the Dirac adjoint spinor sidebar. Sidebar, which is just defined to be I gamma 0 psi star transpose. Okay? And then with that definition, sidebar psi is an invariant. So we're going to stop explicitly referencing transpose, and we'll just throw that into the definition of the Dirac adjoint. So you multiply your original spinor, you complex conjugate your original spinor, multiply by gamma 0, multiply by I, take the whole thing and transpose it, and that is how you construct sidebar starting from psi. And the utility of all that is that the sidebar psi is an invariant. Now this is an invariant that we're going to see a lot. Holy crap. That's like a damn novel. A lot of words on there. Are there any questions about this detail so far? Okay, if you're not completely following it, again, the homework is going to help elucidate this step. And also get you a little more familiar with working with these things, because it's going to force you to think about what the form of these generators are, how things act when they go through exponentials and so forth and so on. So you'll feel a little bit better about a detail like this after you've done the homework. Or I should say the second problem of the homework. And by the way, all of those little identities I'm having you prove in the first part are going to be extremely useful. Everything we're doing is going to be extremely useful when we start doing calculations after we come back from spring break. Okay, so we have now a method for constructing an invariant out of spinors. That's useful. Why is that useful, Marie? Why are we so hot and heavy for invariants?
Because they're the same.
That is a great, nice, wonderful, beautiful thing about them, but what are we going to do with the invariants? What are we going to build out of them? You have a lot of friends. We're going to use them to construct invariant Lagrangians. But what's nice is we can build our Lagrangian using spinors, which are not themselves invariant. But as long as we always put our spinors in this combination, the Lagrangian that we build will be invariant. Okay? And we'll talk a little bit more about why we're focusing on Lagrangians in just a few minutes. However, we can do a little bit more with spinors. Because the gamma mu's are part of the spin story, right? These are important for spinors, but you might notice that the gamma mu's have a vector index on them. So to reiterate, these things are matrices, but they're matrices in spin space. So there's a pair of spinor indices on here which we always leave out, and that is the convention in the literature. We never write spinor indices. So the thing, I'm calling this a matrix, but it's a matrix because it's got two spin indices. This is a vector index in space-time, not spin space. So the appropriate way to think about this object is a vector, a four-component vector of matrices. And they happen to be 4x4 matrices for the four-dimensional case. Okay? In 3 dimensions, what was the analogous thing? Alex. Where's Alex? There he is. In 3 dimensions, what was the analogous thing?
I mean, we consider, wasn't it a vector of matrices?
But how many components did the vector have, and how big were the matrices?
I think it was 3 for the vector and 2 by 2.
Yeah, it was the Pauli matrices, which form a 3-component vector of 2 by 2 matrices. So it's not always the same that the number of components of the vector is the same as the dimensionality of the matrices. That's just a special degenerate aspect of 4 dimensions. Okay, so these gammas are interesting because they live in spin space and in space-time. So they're kind of getting their hands in both pots. And we can make use of that, all right? Before I show you exactly how we're going to do this, I'm starting to use the language of spin space. And I'll probably stick with this because I think it's a good idea for you to, it's a little artificial, but it's a good idea for you to kind of think in terms of space-time and spin space. So spin space has its own index structure, and space-time has a separate index structure. Of course, these two things are related because spin space is a way of describing spinors on a space-time, but we can't use normal coordinates to describe spinors. That was our original motivation for seeking how to construct spinors using Lie algebras, because they're just not as intimately tied to coordinates as other things are. Technically speaking, spinors live on what is called the spin bundle over a manifold. So at each point you define a little spin space, and then you take the collection of those spin spaces throughout the space-time, and that results in what's called the spin bundle. And it's actually perfectly analogous to where vectors technically live. Vectors technically live, if I pick a point on a space, they live in the tangent space to that point. And if I take the collection of all of these, then I get what's called the tangent bundle of the manifold. And the reason why it gets confusing with vectors is that the indices in tangent space you can choose to match up with the coordinates that you use for space-time. And that's called a coordinate basis of the tangent space. You do not need to do that. You can just choose like an orthonormal basis in the tangent space, in which case these indices and the tangent space would look sort of disconnected from the coordinates in the same way that spinors do. So vectors, we often just make use of a convenience that makes them look more intimately tied to space-time, but we actually needn't not do that. And there are cases where it's beneficial not to. So I know you're thinking spinors are really, really weird, but there's actually a certain sense in which you can treat them on a very similar footing to the way you formally treat vectors. And again, for many of you in the room, you're like, what did he just say? But for the few of you who took GR, a lot of these comments are probably identifiable. But anyway, I just wanted to give you... Or maybe not. Maybe they were worse. Oh wow, you know what I just realized? If you use the wrong side of the eraser, it still kind of works. But anyway, I just want you to realize that I'm using the notion spin space. We don't need to work with a rigorous definition, but there is one out there. I just want you to realize it's sort of the way we think of where spinors live versus where vectors live. And that idea is going to carry over exactly when we start talking about symmetries and forces coming from these symmetry transformations, because we're going to have other internal spaces as opposed to space-time or spin space, but more on that when the time comes. Okay. So now an important question to ask is, what is this thing? How does it transform? We should always ask whenever we have an object that we want to work with, how does it transform? And looking at it, you might say, oh, well, clearly it's got two spinor indices, so those transform as spinors, and then this is a vector index, it transforms as a vector. But it's actually, from the way we derive the gamma matrices, it's not manifestly obvious that they have to transform as a vector. And it turns out that you might guess, and let me introduce a little bit of notation, just so I don't have to write these exponentials all the time. If I have a transformation lambda where a vector transforms into a new vector with components given by the lambda mu prime mu, then I'm going to define the spin transformation associated with lambda as the transformation which takes me to the new spinor. And we remember that's e to the I over 4 sigma mu nu omega mu nu psi. So I'm calling this the spin version of the same transformation. So remember, the transformation is basically governed by these parameters. Those are 6 angles, or if you will, it's 3 boosts and 3 rotation angles. But these are the 6 parameters that you choose when you specify transformation. These are the generators of the spin version of the transformation, and this is the total transformation using the exponential map that we always talk about. And I'm just going to lump this whole thing together and say it's the spin version of the transformation, where this is the vector version. And remember, this thing itself you can get from an exponential map, and I don't remember the exact form, but it probably looks something like this. I don't know if they're, I can't remember if they're complex or not, but where these would be the generators that we found for the coordinate forms of these transformations.
So
Yeah.
our spin version takes the spinor index, one spinor index, and transform it.
Yeah, so remember, secretly there's a spin index here. Okay, there's a spin index here and there's a spin index here, we just never write them. So this is actually a spin matrix acting on a spinor, giving me back a spinor. Okay. So what we might guess is that for this thing, to transform it, we should transform every single index in sight. And so we would have an S lambda, maybe 2 of these for the spin indices, and then we would have a lambda for this guy. Okay? But it turns out that that actually is not the correct transformation rule for this thing. Okay? And it's convenient that it's not. In order to get the transformation of a gamma, and I'm not going to prove this because it's really just a lot of algebraic manipulation of symbols that you're not that comfortable with, and it would be very insightful. I'm just going to show you how it transforms. The bottom line is, you either transform the spin indices on gamma, or you transform the space-time index, but you don't do both. And what's nice is that they amount to the same thing. So if I take the inverse of the spin transformation and I apply it to the gamma matrix, and then I apply the spin version of the transformation, here you can just really think about this as transforming these 2 separate indices, but we'll see why it looks like this in just a second. Then this spinor version of the transformation, these are spin transformations acting on the spin indices, is equivalent to doing a vector transformation on the vector index. So you can either transform gamma with spin matrices, spin transformation operators, or you can use the vector transformation. I see fingers, if not hands. Yes?
So would it then be accurate to say that gamma mu is a vector because it transforms like a tensor? So it is a tensor.
It's not, so I want to be careful. It is not a vector. Why is it not a vector?
Well, its components are these 2x2.
Right. I'm going to get there in just, hold on just a second, and I'm going to show you. I'm going to get to something that is a vector. Okay? So just hold on just a second, and you'll see where I'm going with this. Yeah.
Transforming the already transformed vector, or is that?
I'm going to show you why I wrote it like this in just one second. Okay? Okay? So I know you're like, why is he well, first of all, if you just look at the indices, this has to be primed for this right side to agree with it. I mean, the indices always have to balance out on both sides of the equation. If I left this off, that wouldn't make any sense. Okay? But let me show you the utility of this transformation law. Okay? And you'll get a little bit more insight into why this is useful. So let me consider the quantity psi bar gamma mu psi. Okay? And let me transform it. Well, if I just transform the spinors, themselves, or sorry, transform all of them, then the adjoint transforms as psi bar Okay, this was the reason we defined the adjoint the way that we did. Okay, so just to remember, okay, psi bar psi goes to psi prime bar psi prime, where this guy is constructed so that he transforms with the inverse transformation of this guy. Okay, that's why we constructed the Dirac adjoint the way that we did, so that the transformations would cancel. Okay, the problem now is I've got this gamma matrix hiding out in between. But if the gamma matrix transforms according to this rule, then I can just replace this with psi bar lambda mu prime mu gamma mu psi. Well, these are just the lambdas. They're not spin indexed things, so they can come out of this. And so I get lambda mu prime mu psi bar gamma mu psi. Okay? If I just ignore what I know about spinors, and I ask myself, this whole quantity is transforming into that, I would say this quantity is a vector. If I ignored what I knew about spinors here, and I said that just transforms into itself, I would call it an invariant, a scalar. Okay? So the things that we should refer to as scalars are these psi bar psis, and we can build vectors just by inserting gamma matrices into, and you're going to love this name, what I now am henceforth going to refer to as spinor sandwiches. Yeah, Jacob.
Why do we have that gamma mu in there? That's
So I'm just saying, suppose we want to stick it in just for shits and giggles. Can we make sense of that? When we start constructing Lagrangians and equations of motion, we'll find that we need to have gamma mu's in there. I'm just asking, if I stuck it in there, could I make something interesting out of it? And it turns out, and this is the bottom line, I mean, this is the answer to your question. Working with the spinors, we can make scalars, invariants. We already know that, but now we can make vectors. In fact, we can make more general tensors.
okay.
All right? It's just giving us a way to start with a spinor and a dual spinor and then build up interesting space-time objects.
Okay.
Now, the way that you should think about this in your head is as follows, and this might be the most useful thing I say all day. All of these are basically making use of the following in spin space. So the scalar is basically taking a row spinor and multiplying it by a column spinor. So this is 4 components, this is 4 components. And the result is a scalar in spin space. So it's not really a spin thing anymore, it's just a number. But you know that you can take this and you can spread these two things apart, and you can insert as many square matrices as you want. And the result is always going to be a number. That's what we're doing here. The psi bar you can think of as the row vector that always has to cap everything on the left. The psi is the column vector that has to cap everything on the right. And then we can take as many square matrices in spin space, those are gammas. We can take as many as we want and pop a cap in their ass, stick them in between. And the result is always going to be an invariant, at least with regards to spin space. With regards to spin space, it could still be a vector in space-time or a tensor in space-time. Yeah?
Just a quick question. Why did we transform the gamma? Why did we transform the vector index? Because it was my understanding that we just transformed the spinors. So why are we touching to the mu? And the gamma mu? Why are we transforming gamma mu prime?
You're talking about here?
One lower.
Here.
Yeah.
So the way that you should think about this is maybe like that. What is the spin matrix in the new frame?
But wouldn't that modify the two bottom indices that we're not writing out? Because here it looks like we're touching to the vector part of the gamma mu, not the spinor part of the gamma mu.
Yeah, you know what? Martin gets to ask all the hard questions. Okay, so I'm going to backpedal. Sorry, and I'll revise the notes to reflect this. Okay, I'm going to backpedal and I'm going to change my statement entirely. Okay? But you'll understand the consequence of it. It's still going to play out exactly like this. I'm now going to argue to you exactly the opposite of what I said before, which was if we transform this thing, this is me trying to convey to you in certain words what's written in the literature without using this language, and my language is getting screwed up. I apologize, but I want to be right about this. If we transform this, we must transform everything. That's the difference in what I said earlier, where I said you only transform one or the other. But let me write down what that transformation would look like. We know that this is a vector index, so we transform it like a vector. And then this is going to have one guy like that, and one guy like that.
Isn't that just a...
No, sorry. Yeah, and one guy like that.
You're just...
Yeah.
Why is that inverse?
Because he rearranged the equation in the line below.
So, well, no, that is going to be the result that I'll identify. But why it's the inverse, you actually have to derive this transformation rule, and I'll write up the derivation in the notes. Okay, and it's not obvious why it's the inverse, Jacob. Okay. So, yeah, it's not obvious why it's the inverse. I mean, in some sense, it's the same as when you transform the metric. Or when you transform a 0-2 tensor, then the transformation goes as lambda m lambda transpose, which we've seen before, but it's tied to that. But in this case, it just happens to be the inverse. But now you see that if this is the transformation rule for the gamma, then this statement immediately follows. Does everybody see that? If I act from the left with S inverse, this disappears, and I get an S inverse on the left side of this, and if I act from the right with S, this gets canceled, so I have an S. So S inverse S acting on the left and right of the transformed gamma gives me back just the vector transformation of mu. Okay? The reason this is confusing is because no one writes the spinor indices, so you never know whether they're talking about primed indices or unprimed indices. But I'm glad you asked that question, because this is much more comfortable to me than what I was saying before. Yeah?
I was just saying, I think the reason that I had a problem with this is because it just looks wrong to have a bunch of indices and things that are written in terms of matrices, in terms of inverses.
I see what you're saying. Yeah, so you're right. So that shouldn't be there. I shouldn't. Right. Yeah, so technically, and this is what's confusing about it, we then go and erase all those spinor indices because they're never written.
Could you?
So these are matrices that have spinor indices.
So you could go back and put the spinor indices in front of the gammas, but also put indices on those
S's.
Yeah.
Yes. Yeah. but you're never going to see that, is my point, and that's where it gets confusing. Okay. All right, so yeah, so that's the end of Spinors. So ask as many questions as you want because we're not going to turn to something else. Yeah.
So when you're saying with like how we turn Spinors into vectors and tensors, you said can we put any arbitrary 4x4 matrix in between the spinner and the dual spinner, or does it
So
have to
4x4 matrix in spin
be
space.
in spin space? But
Sure, but
by that, do you mean any matrix in spin space being some form of product or sum of Dirac matrices?
so it turns out that the Dirac matrices themselves and certain linear combinations of Dirac matrices form a basis for all 4x4 matrices in spin space. I'm not going to exhaust what that basis looks like, but it's the four Dirac matrices. It's the sigma mu nus, which are hiding somewhere. Those are the commutators of the Dirac matrices. And then there's another matrix which we'll talk about. Well, you saw it in your homework, gamma 5. But yeah, so any 4x4 matrix that you can imagine sticking in here is going to be some linear combination of Dirac matrices. But it turns out, due to the particular properties of the Dirac matrices, that you might say, oh, I'll stick in gamma mu, gamma nu, gamma alpha, gamma lambda, gamma beta, gamma zeta, gamma xi, gamma psi, gamma epsilon. But you're limited in actually what you can do. I think if you try and go more than 4 gamma matrices at a time, the whole thing trivially vanishes. Yeah.
So just a real quick notation thing on that. When you're transforming that third line right there that Mark was talking about, to your right, to the right. Yeah, there. So it makes sense when you go to the transformed, but then how do you get those spinor indices lambdas? Like you go from the transformed size there. Then over one more. Yeah. So where did those spinor indices? Is that just how you define the transformation from those Cybar prime?
Yeah. So remember this? So if you take the gamma out of the story, this is the way to interpret everything I've written. And now we just stick gamma back into the story. Okay. And then we use this nice property of gamma. So I should stress this because it's what I did not say earlier. This is not the transformation law for gamma. This is a useful equation that is satisfied by gamma. This is the transformation law from which you can derive this. Yeah.
So in spin space, you always have just like one like vector change. You get frustrated row by calls and matrices in the middle. How is that still a vector or a tensor, even though it only has one component?
Okay, yeah, that's a good question. So I say this has one component, but if I put a gamma mu in there, this is a one component object that has a vector index. So it's a vector of numbers, which is just a vector. Versus, this is why when Jordan was saying, well, does that mean that gamma mu is a vector? Well, no, it's not quite a vector. It's a vector of matrices in spin space, which I would hesitate to call a pure vector.
Now we're saying it doesn't transform quite, just like lambda mu, you don't get that. It's got this is the...
Right. But this combination, this combination. Because this matrix is going to have indices, this matrix is going to have indices, and together you're going to end up with some 2-index object. This would actually just be a pure number because it was psi bar psi. Okay? Yeah.
Just real quick. On the transformation of the spinner up top, like right there, you transform the real space with the lambda, then you transform the spinner space. So is that saying that the spinner space is completely independent from our XYZ? Otherwise, would those be affected?
So are you somehow saying that this doesn't transform this?
Well, it just seems like you're transforming the spinner space on the spinner, and then you're transforming it with that lambda. And
Yeah.
It seems like is that some sort of statement of the independence of the spaces, or is that they just pull on through affect everything?
So look, if you, It's much like when we transform a second-rank tensor. Every index gets transformed with an appropriate transformation. So if these are space-time indices, then we put a transformation for each of them. What I'm saying here is this is secretly a 3-index object.
Yeah.
And I'm doing this again, and then I'm going to turn around and erase them again. And so this would be like oh my God, this is going to be nuts. A prime A, and then this will be like B prime B or something. Okay? And all I'm doing is I'm putting the right transformation rule for each index that I'm encountering.
Okay.
Now, and this is a point where I think some people got confused in the homework. Even though this is the spin version of the transformation, you define the transformation once. So you say, I want to boost along the x-axis with a speed half the speed of light. That immediately tells you exactly what this looks like and exactly what this looks like. They look different from each other because one is in space-time and one is in spin space, but they correspond to the same transformation.
Oh, okay.
It's just you transform these indices differently than you transform these. In the same way as here, these are the same transformations. Okay, you just have to put a copy of it for each index. You know, if I had two vectors in space, you know, and I called this 1 and I called this 2, and then I had some coordinate system, and then I rotated the coordinate system, each of these would be transformed. Their components would be transformed into a 1' and a 2'. And that's a lot like having the indices here. You transform every index wherever it appears, every free index. Yeah.
So it'd be reasonable to say we're only working with one group. There's one set of transformations.
Right. It is the Lorentz group.
And the spatial indexes versus the spinor indexes are like different representations of that.
Yeah,
So you have to represent that transformation differently, even though they are identical if you go through the...
Exactly. So let me give you yet another way to think about this, okay? So suppose that I gave you a theory where you had two kinds of rectangles that were living. You had these, and then you had these. And then your transformations were going to be transformations that carry corners into corners. Okay? Now you know from the homework that you did early on that the matrices you have to write for this are different than the matrices that you write for this. This is a more degenerate representation. If my theory contained both, then whenever I have to transform this, I would use a different kind of transformation matrix than when I'm transforming this. That's exactly what's happening in a theory that has space-time indices and spinor indices. They're just different representations of the same transformation. So let me give you another idea. So let's just talk about the transformation which rotates by 180 degrees. Okay, it's the same thing. I'm rotating both rectangles by 180 degrees. But the way that it affects this is different than the way that it affects this. Okay? So this you can kind of think of as like a vector index, and this you can think of as a spinor index. And I make that association because spinors know more than vectors do. Okay? So this is the point where I'm actually happy for you to ask as many questions as you can, because I know this is confusing. I think it will help when you do the homework and manipulate these gammas a bit. And then certainly when we actually use this stuff, I think it'll give you a little bit more insight. But that this is confusing is perfectly fine. It should be. This is hard. Yeah.
So it's not double counting by transforming into the vector and this index and the spinor indices?
No, it's not. In the sense that when you transform something, the rule is generally transform every damn index in sight.
Okay.
Yeah. And again, I deeply apologize if you heard me the first time and actually learned it wrong, because I'm sure you all just listen to me and go, yeah, that's it. I myself get very confused in reading about this because everyone leaves off the spinor indices, and you never know whether they're primed or unprimed, whether they've been transformed or not. Okay, so I'm very glad you asked that question. That has gotten a lot of clarity here. So,
How many like representations can we have like side by side? Like this example right here, where we have
Well, we in physics in this subject are going to have scalars, spinors, vectors, and that's usually all we're going to encounter. So our Lagrangians will be built out of those three, and they transform very differently.
So I understand.
We'll have second-rank tensors.
So I understand why we're leaving off the spinor indices, but is there not like a better notation to learn, like to say whether they're transformed or not? Because I feel like it's just.
I know. And the truth. So the truth is that much of what I'm talking to you about transforming is only relevant for understanding what these are. Once we do calculations, when we do Feynman diagrams, we're not going to do transformations anymore. So tracking indices is not going to be nearly as important when we actually start doing the calculations that matter. To understand what these things are, you have to know how they transform. For example, why we have to combine them in these certain ways to get things. So this notation is as confusing as it might be in the formal development of the idea. It's convenient because later on you're never going to need it.
Okay.
Yeah. This is the most important part and the most important way to think about this, because this we will use in calculations. These idea of spinor sandwiches. Okay? Yeah.
Why can't you think about it such that if gamma is prime, the spinor indices also prime, so you not have...
Yeah, you can think about it that way. That's a good way to think about it. So, in the same sense that I told you early on that whenever you have a tensor, all of its indices are either going to be primed or unprimed. You're never going to have them mixed. Then you can use that same idea for the gammas. So even though we don't write the spinor indices, if the mu is unprimed, the spinor indices are automatically unprimed. And if the mu is primed, the spinor indices are primed. Yeah, that's a really good way to think about it. The only object in this class, Claire, which should appear with a primed and an unprimed index would be what? Say it again? I can't hear you. Yeah, the lambdas. Where are they? There, those, because they carry us from the original coordinates to the new coordinates. Good. Okay. Yeah.
So I can see like how these you can give rise to these by just looking at the generating algebras and stuff, but I'm curious as to fundamentally why do we decide to look at these type of objects for like the spin of a particle, and like in quantum one we use the spinors and the Pauli matrices for when we talk about spin.
Spin a half.
Yeah, we never really talk about why you need these types of objects versus just a general vector that's say dumber and a normal Hilbert space. It's like, why do we add all of this?
So the connection between, so you have so what is the connection between the angular momentum of something and the representation of the transformations, or its representation under Lorentz transformations? That's the question you're asking?
Essentially, yeah.
Essentially. So in space-time, I mean, all of what I'm talking about is essentially relevant for the intrinsic angular momentum of a particle or a field. All of that it's internal, so there's no intuitive space-time sense in why you make these connections. The only place where there's ever a space-time connection is if you happen to be working in a problem where there's some dynamical angular momentum. Okay, where you actually have an object that's moving, it's got a spatial momentum p, and then with respect to some reference point, you define the r vector and you form what you typically call the orbital angular momentum. Now, this transforms as what in space-time? If you do a rotation, this transforms as it transforms as a vector. Technically, it's a pseudo-vector because it doesn't change sign under a parity transformation, but we'll talk more about that later. So in space-time, this has an intuitive, it's a vector, okay? But then you know from quantum mechanics that you insert a certain operator for these two guys, position and momentum, and that turns this into an operator, and then when you quantize the theory, you look for the spectrum of eigenvalues of that operator, and it turns out that depending on how much angular momentum you give your system, now this is all orbital angular momentum. This is the angular momentum of the electron as it moves around the hydrogen nucleus, okay? Then depending on how much angular momentum you give it, it has a different spectrum of values. So you assign the L quantum number, and then the ML quantum number goes from minus L up to plus L, okay? This whole quantum program you can freely apply to the internal spin of a particle, but it has no classical interpretation. Like there's no this is a thing spinning. There are actually problems with trying to make that interpretation. That's why respectable physicists don't do it. So, yeah. So, I mean, for example, in quantizing orbital angular momentum, you never see spin a half. You're restricted to integers here, okay? But the algebra of this quantum angular momentum admits half integer values. There's no reason to exclude them unless you're only talking about angular momentum tied to space-time. The minute you go to internal angular momentum spin, there's no reason to exclude it. So you include half integer and integer spin values for internal spin, and then you have to ask the question, well, do particles in nature exist that exhibit these behaviors? And the answer is yes. You don't look satisfied.
Well, I understand that we have and it's like you can fundamentally half spin half, but I'm not what makes the quote Hilbert space that internal degree of freedom lives in manifest itself differently than any other degree of freedom that we really look at. Like most degrees of freedom we look at in a very normal vector type of Hilbert space, whereas if we talk about internal spin, then we have to bring in the whole spinor notion and how that changes. Are there physical things we can see happening that reflect this spinor nature of fermions?
And Stern-Gerlach. Do you know Stern-Gerlach?
Yeah, that's where they that just tells us that they have this internal degree of freedom.
But it tells you that it has 2 degrees of freedom.
Yeah.
2 discrete states.
So is that is it literally just the fact that it's a fundamentally discrete Hilbert space?
Well, I mean there is no classical limit of internal spin. It's always discrete.
Yeah, I just
in space-time, you can take a classical limit where the orbital angular momentum goes over to a continuum of values and you get the normal continuum orbital mechanics. But internal spin is manifestly discrete. It's quantum automatically. I mean, you have to put it in automatically quantum because there's no way to, there's no correspondence that carries you from internal to a classical space-time limit. But no, I mean, and this is what I'm saying, you have to go and investigate, do these things exist? And Stern-Gerlach is you take electrons and you send them through a magnetic field and you find that they split into two beams, okay? And those 2 beams are interpreted as the interaction of this, you have a spinning, again, it's not spinning, but a spinning charged particle, so it has a magnetic dipole moment, and then whether its spin is up or spin is down, it travels a different trajectory in the presence of this magnetic field. Okay? Whereas if it was not quantized, you would expect that the spin could point up or any continuum of values to down, and so your beam of electrons should actually spread, but uniformly. But it doesn't, it splits into two beams.
Well, yeah, but like, couldn't, like, if it's a binary state, then I could just define a finite like a vector, like a Hilbert space where the vectors transform like vectors, not spinors, that's two, like it has dimension 2. Why would I want to define?
Okay, so I think I'm finally understanding your question. Yeah, okay. So the question is why don't we just call spinors the spin degree of freedom some internal vector space that we do transformations on? Why do we have to call them spinors and treat them with all this funky stuff? Okay? And the answer to that would actually be much easier to give you in about 3 weeks. But I'll just give it to you now. I'll give it to you now. We're going to eventually talk about things which are spinors, but they have internal degrees of freedom. They literally have not spin degrees of freedom, but internal, what we call isospin degrees of freedom. So for example, in the weak interactions, we're going to work with these little doublets, weak interaction doublets, and you can actually think of this as a spinor, because these are both spinors, as a spinor with an index that runs over 2 components. And then when I do a transformation of this index, that's actually going to correspond to a weak gauge transformation, which is completely separated from doing a space-time transformation. So you can literally just say it's a vector and there's a transformation. But spinor transformations are tied to space-time transformations. That you do a space-time transformation lambda and it dictates the particular way that a spinor transforms. So we are calling spinor degrees of freedom, we're making a little vector space and we're doing transformations on it, but they have to follow this particular structure because we're not free to independently choose how they transform if we start by saying this is the transformation in space-time. If you never wanted to do space-time transformations, if you never cared about these and you just wanted to define transformations in spin space, then you'd be free to do it as simple as you want. But the reason this story is complex, the reason spinors are hard, is because there is a connection between what you're doing in space-time and what you're doing to the spinor indices. So even though it's internal, it's not completely disjoint from coordinates. That's very different than what we're going to see here, where these are completely disjoint spaces.
Does that make the spin space a subspace of what you do in like regular 4D space, or is that not?
So they're connected to each other. It's not a subspace. Well, you could call it a subspace if you were talking about a really complicated space, which is essentially if you have some space-time and you took the bundle of all possible, if you took the tensor product of all spinor and tangent spaces to a point, an infinite tensor product, then spinors form a subspace of that. But that's the space we'd never talk about to begin with. So I don't think of it as subspace so much. I mean, this technical thing I said earlier is probably the most accurate way to think about it. But yeah, I would think about it as a subspace. Yeah.
So you call them spinors, so how do you get the spin from the spinors? Is that like, are they like, because like the name kind of seems arbitrary, you know, like.
So the words, so that's a good point. So there is a point of confusion because we use the word spin and then we use the word spinor, and they don't correspond to the same thing. Spin is the word that we apply to intrinsic angular momentum of something. It can be spin 0, spin a half, spin 1, spin 2, spin 3 halves. Okay. Spinor is the type of object that exhibits spin a half. Okay. Vector is the type of object that exhibits spin 1. Tensor exhibits spin 2. Majorana fermion, or Majorana Weyl spinor. Not Majorana Weyl. I can't remember the name of it. Exhibits spin 3 halves and scalar spin 0. So you're asking how do you extract the value of the angular momentum from? So again, I mean, this is the one point in the course where, have you taken 320? Quantum mechanics?
I'm taking it, yeah.
Okay, so hopefully in your quantum mechanics class, you're going to treat angular momentum. And you're going to find a general story where if you have angular momentum, then you end up with certain quantum states. And they exhibit certain spectra. And that spectrum of states is going to connect with either things that transform with a zero-dimensional or a one-dimensional representation, scalars, so there's no degree of freedom essentially. You can't transform anything. Or it's going to have two states, spin up and spin down, which naturally associates with two-component spinors, because you're going to do rotations in quantum mechanics, not Lorentz transformations. Or you're going to find something that has three states, 1, 0, and -1, which corresponds nicely with vectors, because they're described by these 3 by 3 degrees of freedom. And then you can go to higher spins. So I can't teach you quantum mechanics in this course, but that's a connection that you should make in your quantum mechanics class. Whether your teacher does that or not is up to them. But that's where the answer to that question lies. Okay? And so look in your quantum book if you want to look ahead and try and make that connection more strong. Okay? But I can't play that whole story out for you now. It's a little too long and complicated. All right, I'm going to move on, I think. Yeah, okay. All right, well, the good news is that I've only got 4 more pages of notes, so we're good for today. We're going to now completely change gears and begin to talk about what we're ultimately going to do with this stuff, okay? So, I have this joke in my notes, so I'm going to write it on the board. Okay, so somebody should make a shirt. All right, shut up. Make it. Look, I had to put out the damn nuts in a saran wrap shirt. I don't want to hear it. Anyway, okay. So,
My joke was classy.
have classy jokes. I got some pretty crude ones too, but I like classy jokes. Okay, so when you approach dynamics in physics, there's many different ways to do it, right? You can use Newton's laws. You can use energy and momentum. You can use Hamiltonian dynamics, Lagrangian dynamics. In our pursuit, it's actually going to prove most fruitful to come at everything from the action principle in terms of a Lagrangian. So we're going to make use of action principles, and I'm going to the best of my ability, remind you of how action principles work in a two-dimensional example, and then we'll talk about what this looks like in more general context next time. So I'm going to take a Lagrangian in 2 dimensions for a particle. So this is a classical particle. And I should say, one of the reasons why we use Lagrangians in this course is because Lagrangians are, in my opinion, they're the most powerful approach to dynamics, because you can do particles, you can do fields. You can do classical, you can do quantum, you can do relativistic, non-relativistic. You can do it all with Lagrangians. Okay? So this is nice because I can give you examples from context you're familiar with, classical particles, all right? But then we can immediately carry the results over to what we need, which is relativistic fields. So the Lagrangian is, for a particle, it's written in terms of the coordinates of the particle and the velocities of the particle. And I'm not going to worry about the precise form, but what I do with that is I form the action. Yeah. So the action is called a functional of the particle's path, x of t. Okay? So this is a functional. Anybody ever heard that word? Okay, so you're familiar with functions. And the principal role of a function is, if I give you a value of its argument, then that returns a number. So if you feed a number into a function, you get a number back. Okay? Functionals are such that I feed the functional a function and I get a number back. So functionals are much like functions in the sense that they give you numbers, but the difference is what you feed them. So you might go, what the hell does a functional look like? Well, here's a functional. Okay? You give me a function, say x squared. I get a number back. Yeah?
So don't we a lot of times hide functionals inside functions by saying like x is a...
Yeah, you do. You do. But generally, what I'm interested here, though, is a map from functions into numbers. Because what we can do, now that we have functionals on the table, is we can play a game very similar to what we do with functions. So if we take functions, then we know that we can, by taking df dx and setting it equal to 0, this gives us the values of x which do what? Extremize the function f of x. That is, it corresponds to maximum, minimum, or saddle points. Okay. We can do an analogous thing with functionals. So if we take a functional, we can take what I'll define as the derivative, and we'll talk more about what this looks like later. We can take the derivative of the functional with respect to the function, and by setting that equal to 0, it gives us the functions which extremize the functional. Again, corresponding to maximum, minimum, or saddle points. All right? Now, what I'm talking about in terms of the values here of the functional are numbers. Okay? And I know whether a number is bigger than another number. Well, I mean, I say that because does it make sense to say whether a vector is bigger than another vector? Yeah. In what sense? Right, but that's a number. Okay? So when you want to talk about extremizing, finding maximum and minima, it makes sense to talk about numbers, comparing the values of numbers. Okay, this number is definitely bigger than that number. All right? But what do I keep saying we want our Lagrangian, and hence our action, really, to be? Invariant, a number. Okay? So, in order for this whole extremization program to make sense, our action needs to be a number. But of course, a number is invariant, so if I do a transformation in what this action is built out of, i.e. the Lagrangian, then that thing better not change. The number better not change under a transformation. Okay? Now what's amazing, this is just a curiosity. This is like a mathy generalization of what you do with functions. But what's astonishing is that if our functional is defined as the integral of the Lagrangian over a time interval, then demanding that the action vanish, or the variation of the action vanish, leads to conditions on these x of t's which describe the physical motion of the system. This is Hamilton's action principle. So this is just a mathematical thing you can do, but there's physics in this. this observation was initially just made by constructing these action functionals, varying them, setting the variation equal to 0, and then getting equations out of them. And those equations happen to describe the physical systems. It wasn't actually until quantum mechanics that this could actually be given some theoretical underpinning. And we'll talk a little bit more about that next time. Okay? But, yeah. Yeah, so next time we're going to start by actually taking this two-dimensional example, extremizing it, taking the variation, setting it equal to 0, so I'll show you what all these words mean, okay? And then once we set the variation equal to 0, we're going to get a set of equations, which we typically refer to as the equations of motion of the system. And of course, in this paradigm, those are what are often referred to as the Euler-Lagrange equations of motion. So I'll do this whole variation procedure for this simple two-dimensional classical example. Once we've got the Euler-Lagrange equations, then we're going to be able to take it and just infer what it all looks like for relativistic fields. Okay? Yeah. Is this about this? Let me make an announcement because I know people are starting to pack up. We're not going to have a quiz on Thursday. We're going to do it next Tuesday because I didn't get nearly as far as we needed to. But that doesn't mean that you should hold off on starting your homework, because as we start moving into these fields and actions and so forth, or these actions and equations of motion, you're going to want to kind of get as comfortable with it as you can before we move on. Go ahead.
Isn't your functional depend on y as well?
Yeah, this should be a functional
X the vector.
Yeah, we'll do this next.
Everything's a vector. Or a tensor.
So just because this is something that's always on me, mechanics,